In this lecture, we would discuss the notion of operation on sets and various properties on operation on sets. So basically, there are two standard operation on sets, that is union and intersection. So let us formally define these two operations. So first we discuss union of sets. Given two sets A and B, the union of A and B is the set which is denoted as AUB equals, it's a set of all x. This x is coming from the universal set such that x is in A or x is in B. Now you all know the definition of disjunction. So this is basically disjunction of two statements, x is in A and the other statement is x is in B. So that is x belongs to A union B if and only if, this is the definition. So if and only if x belongs to A or x belongs to B. Next we define intersection of sets. The intersections of the given set A and B defined as A cap B, that's a notation, it's a set of all points x in the universal set such that x belongs to A and x belongs to B. So x belongs to it's a collection of the set which lies in A as well as B. So that is x belongs to A intersection B if and only if x belongs to A and x belongs to B. So these are the properties of union of two sets and the intersection of two sets. Here is an exercise for you. There are two questions for you to think and you can in fact justify it. So if A is a subset of B, then what can you say about A union B and A intersection B? You must be knowing a very old fashion of drawing the set as a Venn diagram. So you can draw this, the meaning of subset. So you can draw this geometrically and you can visualize it, guess the answer and justify it. What do you mean by saying x does not belongs to A union B? So this is exactly the negation of the statement x belongs to A union B. And you know what is, when do we say that x belongs to A union B? Same way, what do you mean by saying x does not belongs to A intersection B? So this is negation of the statement x belongs to A intersection B. So you would negate the definition, the statement x belongs to A and x belongs to B. Another very small exercise and a simple exercise. You are given two sets, the first problem A and B. A is a set of all points x comma y in R2 with the property that x square plus y square is equal to 1. So we can see that these are the points on a unit circle with radius equal to 1 and the center is equal to 0. And B is the set of all point x comma y in R2 with the property that x is equal to 1. So this is in fact the straight line parallel to x equal to 1. So it's parallel to y-axis, right? So the question is find A intersection B. X equal to 1, is it parallel to y-axis? Divisible by B, A and B is a set of integers which are divisible by 3. Find A intersection B. And the third one, A is a set of all x in R with the property that x square is greater than or equal to 0. In fact, you can simplify this set further, which are the real number whose square is always greater than or equal to 0. And B is a set of all x in R such that their x cube, such that x cube is greater than or equal to 0. Then the question is find A union B and A intersection B. Obviously these are the subset of R, so A union B and A intersection B will also be a subset of R. Now we would see some standard properties of this operation. So first property is the associativity property. We have a associativity property for union as well as the intersection. Suppose A, B and C are three sets, then first property says that A union B union B union C, A union B union C in bracket is equal to A union B in bracket union C. Second one, A intersection B intersection C in bracket is equal to A intersection B intersection C. So both these properties says that whenever we have we are computing a union of three sets or intersection of three sets, we can compute any union or intersection first. And the proof, I would prove the first statement, and in a similar way you can prove the second statement. So basically in the first statement we want to prove that the set on the left hand side and the set on the right hand side are same. So to prove this, we use the definition. When do we say that two sets are equal? It is when both of them are subset of each other. So I would first prove that this A union B, A union bracket B union C is a subset of A union B in bracket union C, and then prove the reverse way around only using the definition of union of a sets. Okay, so let's see the proof. So to prove that something is a subset of one set is another subset of another set, we just take an arbitrary element in the given set and prove that it is also belongs to that set to which we want to prove that this set is a subset of the other set. So that's how we would start. I would start with an element in A union B union C. A union in bracket B union C will prove that X also belongs to bracket A union B union C. So this we would accomplish only using the statements or the definition. So first, when I say X belongs to A union and bracket B union C, this is same as saying X belongs to A or X belongs to B union C. So that is again same as the definition of X belongs to B union C. X belongs to A or in bracket X belongs to B or X belongs to C. Now we all know the property of OR. Whenever I say that the statement having OR is true, that means at least one of the statement is true. So in that case, in this case, you have that this is true or this is true. So that means either this will true or this will true. So I can split the bracket because you will see that there are two ORs that are connected in this statement also. So if I say that this is true, that is same as saying either X belongs to B is true or X belongs to C or is true or both. So that here it would be same as saying without writing the bracket. So we have X belongs to A or X belongs to B or X belongs to C. And now again you can rearrange the bracket wherever you want, again using the definition of OR. So that would mean, this would mean X belongs to A union B, and this is separated by OR. So X belongs to A union B union C. So this proves that A union B union C is same as this is a subset of this set, and in a similar way you can prove that this, that is A union B, the other way around, which says that proving that A union B union C is equal to A union B in bracket union C. And the second one can be proved in a similar way. It's going to have N, and you just have to open the bracket and remove the bracket and rearrange the term the way you want. So I would leave it as an exercise. Now these are the problem. In fact, this can also be considered as a standard property, as we would use this, proving whenever we want to prove that one is a subset of other. Suppose B is a subset of C. Prove that for any set A, we can take the union on both the side as well as we can take the intersection on both the side. A union B is a subset of A union C, and the second statement, A intersection B, is a subset of A intersection C. So let's see the proof. So again, this is simply a subset, so any element over here should lie over here. So I would start with any arbitrary element in A union B. So let X belongs to A union B. This means by definition X belongs to A or X belongs to B. So now we know that B is a subset of C. So this X belongs to B. Whenever X belongs to B, that would imply that X will be in C, as B is a subset of C. Again, using the property of subset. So the same statement can be written as X belongs to A or X belongs to C, because whenever X belongs to B, X belongs to C, and that proves us that X belongs to A union C, and proving that A union B is a subset of A union C. Now the second one, again I leave it as an exercise. It's a similar problem, only thing in place of OR you are going to have an AND. So I would that left as an exercise. If A is a subset of C and B is a subset of C, then show that A union B is a subset of C. Okay, if A is a subset of C and B is a subset of C, then its union on the right hand, see, if they have a common major standard parent set, then the union will also be in that set. That's what the first theorem says, and first property says. The second property says that if A is a subset of B and A is a subset of C, so if there are common set which are contained in two different sets, then A will contained in the intersection B intersection C. So how do we prove this? So I'll prove the first one. Suppose I want to show that A union B is a subset of C given this. So if X belongs to A union B, then X belongs to A or X belongs to C by definition. But we know that A is a subset of C as well as B is a subset of C. So X belongs to C or X belongs to C. Saying this statement is true, it is as same as saying X belongs to C, because in both the cases we have OR. So therefore A union B is a subset of C. Now proving the second statement, suppose I start with X belongs to A. I have to show that X belongs to B intersection C, that is X is in B as well as X is in C. So we know that A is a subset of B and A is a subset of C. So whenever X belongs to A, then X belongs to B as well as X belongs to C, as A is a subset of B and A is a subset of C. So any element over here will gradually lie in B as well as C. And that exactly the definition of X belongs to B union B intersection C. So therefore we prove that A is contained in B intersection C. Now again, these two property are simply used when we want to take a union of two sets and show that it's a subset of another set. Another standard property is a distributive property. So which says that for any set A, B and C, A intersection B union C is same as A intersection B union A intersection C, and if I change the role of intersection and union, again we would have, that is A union B. A union B intersection C would be same as A union B intersection A union C. So the proof for this, again I would be proving the first statement. Second similarly can be proved. So I want to show that this set is equal to this set. So I would and this that is, so I would be showing that this set first is a subset of this set and the other way around. So first I'll start with any element in A intersection B union C, and I would be applying the property of intersection as well as union. So first, since this is computed separately, first I would apply the definition for intersection. So this would mean that X belongs to A and X belongs to B union C. And now you apply the definition of B union C. So that would be same as saying X belongs to A and in bracket X belongs to B or X belongs to C. Okay, now remember that see this, if I consider this as one statement, if I consider this as another statement, then it's a conjunction of these two statements. So whenever I say that this statement is true, that means both the statement have to be true. This is true, x belongs to A is true, and x belongs to B or x belongs to C is also true. But the second statement itself is again a compound statement with the connective or. So this statement being true would be same as saying at least one of them is true. So what I'll do is that, so that means this have to be true, and again this have to be true. I mean at least one of this has to be true. So if I write down this in terms of or, this will always be part of the compound statement. So how do we write down this? I can say that x is in A and one of this will be definitely true, so that or both will be true. So I'll take one of this together, x belongs to B, or x belongs to A and again one of this will be definitely true, so x belongs to C. So that would make sense saying this way. And now this whatever is in bracket is exactly your definition of A intersection B. When do we say that x belongs to A and x belongs to B? X belongs to A intersection B, or this is same as saying x belongs to A intersection C. So this x is in one set or x is in another set, so that is same as saying x is in union of these two sets. So this A intersection B is one set, A intersection C is another set, so we have this. So this proves that A intersection B union C is contained in A intersection B union A intersection C. So next we need to show the other way around, and to show the other way around, again you can formally go with the typical way of showing one set is a subset of other, but here we can use something shorter than that, that is using the previous property. See, we know that B is a subset of B union C. This is trivially true. You can see that B union C is something bigger and it also contains B. So therefore B is a subset of B union C. C is a subset of B union C. This is true, right? So now using the previous property, what would happen is that B okay, first I'll intersect with A on both the sides. So I will have B intersection A is contained in B union C, that is A intersection B will be contained in A union B. I'm taking intersection by A on both the side. We get A intersection B contained in A union this should have been intersection. Okay, so this is an error, so please take a note of this, because we are taking intersection by A. So this is A intersection B union C, and again similarly A intersection C is contained in, this is correct, A intersection B union C. Okay, so please take this correct this error, and you see that this A union B is contained in the set, and A union C is also contained in the same set. So I can use the previous property which says that whenever this happens, their union also contained in that same set. Okay, so this is intersection. So that's why we should have A intersection B union A intersection C should contained in A intersection B union C. And proving this from 1 and 2, now we can say that both the sets are equal. The second one left as an exercise. Operation on a finite number of sets. So far we have defined union and intersection of two sets. Now this can be extended, for a finite number of sets. So here we would see that extension and the definition of union of finite set and intersection of finite set. So first see union of finite set. So suppose we have n set a1, a2 till an. The union of this ai, where I is varying from 1 to n, okay, this is the notation. Bigger union running from I equal to 1 to n. I is the variable that is used, that can be changed. So ai, okay, this is a set of all x such that this x belongs to some ai, or in other word, there exists at least one ai such that this x is contained in that ai. So that is same as saying there exists k in this running set 1 2 till n such that x belongs to ak. So that is x is in x is in union of ai running from 1 to n if and only if x is in ak for some k belongs to 1 2 till n. So I hope you understand, you have understood this definition of union. Whenever I say that x is in the union of finite set, that means x is in at least one of those sets of whose unions you have taken. Okay. So intersection of set, again, you know the definition of intersection of two sets. We say that x belongs to A intersection B if x is in A as well as x is in B. Now that term is extended further. So if I want to take intersection of say some finite set, intersection of n sets, then its intersection will be set of all the elements which belongs to all these AIs, which is in A1 as well as in A2, and this goes on till AN. So it's a set of all x such that x belongs to AK for all k in this set 1 2 till n. So therefore I say that x is in this intersection of AI if and only if x belongs to AK for each k running from 1 to till n. That is same as saying x belongs to each of this AI. Okay, now this is a similar exercise which you can prove very easily using the idea. So if we have this set A1, A2 till AN, the first thing that you need to prove that each of this AI is contained in the union of AI, and intersection of AI, I running from 1 to n, is contained in each of AI. Very simple. And again, you can see that intersection of AI is always a smaller set, so that is always contained in union of AI. Disjoint sets. So the two sets are said to be disjoint if the intersection is empty, that is, if A and B do not have any elements in common. We have some example. The first example is a set of even integers and set of odd integers. Set of even integer is a set of all integers such that m is that integer is the multiple of 2, and set of odd integer is the set of all integers m in z such that there exists k in z such that m can be written as 2k plus 1. So this two sets does not have any common elements. We cannot have a integer which is both even as well as odd. Again, this is a set of all x comma y in R2 such that x plus y is equal to 0, and this is a set of all x comma y in R2 such that x plus y is equal to 1. So this are the points. Both these sets denotes the points lying on a line, this passing through the origin, and this is not passing through the origin, and they are disjoint, and in fact you can prove this. Now basically when we want to show that the two sets are intersection, we prove it using contradiction. We assume that there is at least one element, and at the end we get certain observed result, or at the end we contradict to the assumption itself, proving that our assumption is wrong. Okay, so that is the typical way of showing that something is disjoint. So here's a question for you. Suppose m and n are distinct positive integer. If a and b are sets of integral multiples of m and n respectively, then are a and b disjoint? Thank you for watching this video and have a nice day ahead.